Alrighty, a few more people have joined. Let's go ahead and get started. We have a lot to cover, and the recording will be available. So thank you for everyone for joining the webinar. Today we're going to talk about uh, cost of Kafka and effective strategies for reducing the total cost of operating Kafka within the cloud environment. My name is David Karamgard. I'm a principal sales engineer here at Stream Native. Let's go ahead and get started. So again, we're going to cover material that was published in a white paper that's available for free download. So here again, if you haven't had the chance to review that white paper, if you want to follow up later and have some details around this, including some additional charts and graphs and data, I encourage you now to scan the query code there shown on the screen. That'll take you to a sign up page where you can enter a few pieces of information, your email, and you'll be able to download your own copy of this cost-effective white paper, approximately 30 pages covering everything that we'll cover here today in the webinar. Hopefully everybody has a chance to do that. We'll go ahead and get started here. So really what we're talking about, Kafka has been highly adopted. It's been around for over a decade now. It's used throughout major industries in a lot of different places for use cases. It started obviously with log ingestion, but has since evolved into event-driven architectures, et cetera. And primarily, it first started out when Kafka came out, everything was running on-prem. People would buy their own racks of servers. They'd host it in a data center. So it predated the heavily shift to cloud. So it wasn't architected necessarily for the cloud, and that has hindered its adoption into the cloud. You really want to host all of your important services on a major cloud provider, to give the guarantees, the uptime availability, and sort of offload that infrastructure spend that you needed to have investment to host your systems. But there's been, some issues related to that, cost being primarily above those, right? It's really 90% of hosting Kafka deployments in the cloud are related to the infrastructure itself within your cloud provider and not necessarily the software line underneath. And so in this webinar, we're going to talk about some of the different cost centers and how you can optimize your cost savings in those areas and cover some strategies that you might be able to implement, whether you have an existing Kafka implementation or if you're evaluating Kafka vendors and you want to sort of pick different products among the two. You can have a more educated point of view in that regard. So taking the 10,000 foot view of Kafka, right? It's a messaging system. Obviously, it ingests messages from multiple producers, deployed everywhere outside the internet, within your network, etc. It stores them on local disk. And again, this is a traditional model, stores everything on local disk. And then when the consumers come to consume those messages, again, sends those data out over the internet to those consumers. And each step along the way incurs some cost, right? There's a bit of associated cost with each one of these. And we can really break it down into three distinct categories, right? There's networking of the data ingress and data egress, potentially some data replication in between. There's some cost related with the hosting of the brokers themselves, the computing. And then obviously there's some storage, whether it's a local attached storage or block storage. Those are your three different cost centers, and you can break that down accordingly. Now, if you were to make some basic assumptions here, so again, let's just say you're looking at this here shows the hypothetical infrastructure cost for a traditional Kafka deployment on AWS, where you deploy three brokers, each in a different AZ availability zone for for redundancy and high availability, using attached local SSD quality storage, EBS volumes to store 100% of the data and keep that data for a 24-hour period only. All networking of ingress and egress is done over the public internet. In this regard, you're using, again, attached SSDs, and the brokers are just your traditional sort of run-of-the-mill M6 X large computing nodes, so nothing really exotic, sort of your basic memory optimized nodes. And it's assuming that each message is read just once, right? So as you can see, there's trends start to come in as you increase the data volume, right? If you're trickling along at 1 megabyte per second, your storage costs are very low and your compute is sort of a fixed number. You can see that stays static up until you get to larger workloads because you need three brokers. And so sometimes you're paying a little bit more for compute than you actually need. But as you start getting, a little more moving along in there, sorry, you can see the network starts to dominate in this cost, right? Because there's an influx point where the network really starts to take over, even at a very small number of 5 megabits per second. You can see networking is almost, is more than 14 times your storage cost. It is more than your compute cost, and it quickly, and it doesn't get better as you scale up. The more you scale up, the more this light blue bar increases, which represents your networking cost, right? And this is again just data going out one time, so you can see this is where your cost is primarily driven by. And you really want to, if you break that down as a percentage of total cost, you can see, looking at it differently, you can see very quickly that, uh, their networking costs quickly rise up to over 85%. And while your computing costs shrink and sort of level out as a percentage, and same with storage, right? So you're trying to see, you know, where when you're looking at trying to optimize these things, the best strategy is to first understand what the problem you're trying to solve and prioritize your efforts accordingly, right? So if you're looking at the same chart we showed in the previous slide as a pie chart, as a whole percentage of, where's my costs come from if I'm running a cluster of this size, that big green circle there indicates networking. Again, this is a public, if you're using public network to come in, you can see it as the dominant factor. And you should prioritize your, your cost cutting efforts based on the actual percentage of the spend by category, right? So stated differently, if you were able to just decrease your networking costs by 10%, which is 85% of your total spend, that's the equivalent of basically eliminating your entire computing costs entirely, just because it's such a larger factor. So go for, when you're optimizing your Kafka cluster, look at the areas first for most bang for your buck, is really what we're saying. So networking is by far your biggest cost center. So let's look into different ways to optimize that and where data costs come from, right? So networking costs within Kafka really fall into one of these three categories at a very broad level. So again, the first one being the data transmission itself. This is the raw bytes coming in, you're publishing to Kafka, the data you're consuming and sending out to your consumers. That all that network traffic and that network costs we consider network data transmission. It is the core feature of what Kafka is doing. So it is sort of a given that you have to have this. This is going to be part of your cluster, and it's something you have to be aware of as well. Another kind of hidden part of the networking cost that is less obvious is the data replication cost. So again, Kafka uses a leader follower mechanism that's built into the architecture of the platform itself. And there's some costs associated with moving the data from the broker who's the leader in one of the availability zones and making that data available in other availability zones for redundancy. That has to travel over network in some capacity, and there's costs associated with that as well. And then last but not least is the data movement costs associated with a data rebalancing event. When you're adding or removing, topic partitions or adding brokers, et cetera, there's a data movement rebalance that has to occur. So again, if you, for example, have 3 brokers running in a JZ, you add a 4th broker. At this point, the data has to be moved onto that broker so it can start serving requests. That data movement from the existing brokers to that newly added broker goes over network, and that incurs some networking costs as well. So that's where your costs all come from. And we'll focus on the next slides on how to sort of break these things down and evaluate these uh, values very simply. So for now, we'll just keep keep the model very simple, and we'll assume that there's just a single cluster resides within a single region. And again, you have brokers in multiple AZs, showing you here that you can have where you locate your consumers relative to the broker has a significant impact on your data transmission costs, right? So the ability to, the closer you can deploy your consumers to your brokers, the less it's going to cost you in terms of network traffic and what they charge you for network traffic within your cloud provider. So again, if you can host it within the same AZ, it's very inexpensive. If you can post it within the same region, again, while it's not as cheap as within the same AZ, it is still significantly less. Interregional, from one region to another is going to have a higher cost as well. And then last but not least, again, the first uh, option we talked about was the public networking. So that's exposing your Kafka brokers over the public internet. The ingress for this particular usage is free. They let the data come in very free, but it is very, very expensive to send the data back out. So having consumers have to consume over public internet is one of the most costly ways to transmit data back and forth. And this is borne out sort of in the costs across all cloud providers. While they're charged slightly different amounts per major cloud provider for these tiers, you can see that there is a definite correlation between internet costs being the most expensive, interregional being second, across AZs being third, and within the same AZ being relatively inexpensive or free, right? And so now, based on how far you travel, that's going to impact your networking cost. And again, you want to utilize networking for data. When you're utilizing the networking for data transmission, you want to optimize for the placement of these consumers based on where, minimizing your networking costs. So if you have the option between putting a consumer out in the public internet or bringing it into within that same region or within that same AZ, obviously every time you can shift it into that same AZ, you're going to save money, a significant amount of money per gigabyte, as you can see here shown in this chart. But a lot of times it's not that simple, right? So it's easier said than done. If you want to have going this way. What's going on here? There we go. So if you want to use, public networking, sometimes you just don't, if you're using a hosted solution, public networking is your only option. This is because you have, information available there. Again, the infrastructure is rather owned by the cloud vendor. It's a hosted solution. They're not going to let you run software within their cloud account. Therefore, you're going to have to incur these larger egress costs. Ingress is going to be free, but egress costs, the number of times you read those messages is going to cost you, again, on AWS, for example, 9 cents per gigabyte. And so this is something to consider when you are looking at these hosted solutions. They may be, have some cost savings benefits until you start looking at consuming that data. And then, as we saw in the first slide, those costs can quickly get out of hand, even at moderate data set size. So they become very, very dominant as far as cost is concerned very quickly, right? So again, looking at the difference in these access between these different transmissions, if you're all to take that same number, you can see that the ingress cost is free overall. Again, that's a flat line. If you're able to do it, again, if you have an ingress fan out of just one, then that cost goes up. But again, it's driven by a factor of the number of times you read. So if you read that data 5 times or 10 times over the public internet, it's 5 to 10x factor of cost, right? So this is hosted solutions that only offer public networking, or if you do it yourself, hosted solutions, and you only expose that over public internet. The analytical use cases are not good. Data sets that are read multiple times are not good for this environment. They're just going to incur a very, very large networking cost very, very quickly and become problematic for you. And your goal is to optimize this cost so that you can, spend the dollars where it makes sense and not just give the money to your cloud provider for sending the data out over time. So obviously, we recommend using private networking or avoiding the use of public networking as one of your best choices for that. So setting up your cluster within an environment that you have access to, being able to co-locate your applications within a networking layer that makes more sense. This diagram here shows, for example, Stream Data's own what we call our Bring Your Own Cloud offering, which we'll talk about a little bit, in which you host your Kafka cluster and you host our Ursa engine within your environment, allowing you to then access it directly through internal load balancers, through a VPC peering, through within the same region or within the same AZ, and have a much lower egress networking costs, and sometimes even free, again, within the same infrastructure. So this is a very, again, most bang for your buck you get from doing this type of deployment model. and you will save a significant amount of money from setting this up. While at the same time, you can still theoretically expose the information over a public endpoint if you need that. It's not an either or choice. But again, you can optimize it, right? So for those who need public, you can still make it available, but you should shift the bulk of your application deployment into a more cost-effective networking region to save on those costs. And how much cost or savings are we really talking about there? Again, I showed you in the previous slide that it was, relatively, 9 cents per gigabyte on internet and maybe a penny on going out. This chart here sort of shows you the difference very, very quickly. Again, for even the fan out ratio of 1, reading the message one time can save you a significant amount of money. Again, avoiding that internet tier saves you money, but this option is only available in what we call BYOC, or bring your own cloud sort of Kafka solution, something that's requires you to host the entire infrastructure within your environment. Again, if it's you do it yourself or if you're using a vendor, being able to do this inside your own cloud environment saves a significant amount of money, specifically in egress. Specifically, again, based on the different tiers, it's either, cloud provider 89, 81 or 75% respectively for AWS, Google, or Azure in terms of costs. And again, this is on cost savings on the most costly part of your deployment, which was 85% of the total cost of operating it, right? The downside is, unfortunately, if you start hosting your clients within these non-internet regions, they start charging you for there's ingress costs for versus for networking data transmission where there was not over the public. Again, egress was free over the public internet, but here they're going to charge you a small amount for ingress. So just be aware of that. But it more than offsets the savings here, more than offsets this ingress cost as well. So looking at another, option for or networking costs is the data replication. We talked about data transmission, data replication, right? So again, Kafka uses that leader follower mechanism. So, the more to ensure high availability, you generally deploy your brokers across multiple AZs. You make sure that there's a leader in one AZ rather, and copies in other AZs. So that way you have a copy of the data everywhere. Again, and this data replication is a factor of your replicate, the number of AZs you deploy within there to have that data transmission as well. So again, if you start sending this data, you can minimize. So there's a cost associated with each one of those bytes being sent between inter AZs. And if you want to reduce the cost, you can start. But one strategy is to just reduce the number of AZs over time in which the cluster is deployed. But the trade-off is, as you start removing these AZs, you're going to potentially have a significant downtime if that only one of those two AZs goes down. You're putting a lot of eggs in one basket, and you could really miss your SLAs as far as uptime are concerned. So generally, we don't recommend that, but you can minimize that data replication traffic if that's something you really, really optimized on savings for that. Now, let's see here. This isn't working. Now, some offerings have come around recently to the market, Kafka offerings specifically, that avoid data replication costs and storage costs, and we'll talk about that in a bit, where they bypass writing data to local disk entirely and store everything into a object storage, cloud-based storage underneath the covers, right? So this not only saves the storage costs, which we'll talk about in a bit, but it also allows you to save that data replication cost, because you no longer need to enable leader follower replication in these scenarios, because you're depending on the underlying object storage is internal replication mechanisms to make sure that data is available across different AZs. Right, so we're showing in this particular example, if you have 3 different brokers and different AZs spun up, and the data comes in on the leader, they're in AZ number 1, it writes the data to S3. If that broker goes down, that region goes down. Any one of those different brokers, for a replica, it can just go back and read that data from S3. So another broker in a different AZ can read that data very quickly, and you have not been charged for that replication traffic. Again, S3 took care of that for you. But again, there's some trade-offs associated with this approach and these architecture designs because there's latency incurred when you're trying to buffer up this information. Basically, the strategy a lot of these serverless or these object storage only platforms use is to buffer up the data in smaller chunks and write it into S3s so it's a little more efficient. And this is because there's an additional cost occurred with every time you do a put or get operation on these object storage stores. And you want to make it more efficient as well. So again, you try to balance the costs by buffering these things up. But again, the trade-off is latency on the producer side. And again, on the consumer side, there's some additional latency involved. Right. But having said that, this is your potential savings if you take one of these strategies of either reducing your leader follower replicas from 3 AZs to 2. And there's a big difference as far as what you use as far as cloud provider as well. So this is what you can potentially save at different workloads. Not insignificant to say the least, but again, at smaller workloads, it becomes very, very negligible, right? And so it's really up to you whether it makes sense. Roughly, if you're at the 50 megabit per second day, which is a significant workload, that's a very, very large cluster. You're only paying $40 a day for have a third AZ versus a second AZ. One thing to note is if you're an Azure customer, they've recently reduced their inter AZ across AZ network traffic to be 0. So no matter what work size you are, you can have a 0 cost for that networking cost. It becomes much less, right? So you're able to basically get the benefits of a serverless S3 backed avoidance of that networking costs while not having to pay a latency penalty if you host it in that type of cloud provider. So it's a very, very good option for people who use that as well. And then last but not least, the third data rebalancing or networking costs is from data rebalancing, right? So again, a common scenario, you have a Kafka cluster, you have 3 nodes available, they're starting to get full, and you add a new broker, right? And so data obviously first has to be shuffled over onto that particular broker in order for it to start serving data and requests. And so this scenario, right, we take these little light blue slices of data, roughly a third of the data on each of the existing brokers, and shift it over onto that newer broker. And so you can see there's, assuming you get optimal data balancing, you're moving roughly 25% of your data. And that is, again, going across an AZ potentially. So again, while it's less predictable and I can't show a chart that says this is going to be your daily cost, this is sort of an ad hoc cost that's hidden when you try to make your, dynamically scale up your cluster or scale down your cluster to optimize your compute costs. The counterpoint is that you're going to incur this networking cost and maybe negate any savings you might have from, optimizing your brokers by spinning it up or spinning it down. Again, if you decommission a broker, you want to have the data replicated back and move somewhere. So there's a networking cost associated with that. Additionally, in addition to just dollar costs, there's also some other hidden factors associated with this data rebalancing movement. First and foremost being downtime. Using a traditional Apache Kafka deployment, moving a significant amount of data, during a rebalance over even a very, very large network, 10 gigabit network can take hours and hours. I've seen published online where large Silicon Valley company did a rebalance on one of their clusters and they were down for 12 days because of the sheer data volume on that, because everything freezes, everything has to be moved, right? So it really, really makes it harder to, impacts your elasticity. You can't spin your cluster up or down. You're going to incur some downtime if you're trying to scale up or scale down. As I mentioned before, networking costs come into play because you're sending that large amount of data, 25% of it or whatever percentage it is based on your partition number. It's going over the network traffic, and that's going to incur a cost as well. You're going to have people on site to sort of need to monitor and manage these SRAs. For example, if you're doing it yourself or open source and you have a team of people that are going to have to watch this process, make sure it goes well if anything goes wrong. So there's some hidden costs there. Or if you decide to choose a vendor who offers some sort of replication or rebalancing things under the covers, be aware that those generally are an upsell or a higher higher price license. And so that factors into your total cost of ownership. If you're trying to avoid this issue, you might end up having to pay just as much in licensing costs as you were if you were just to incur that networking cost and avoid the rebalance to begin with. So lots of hidden costs in that data rebalancing thing, and it's definitely something that comes into play with your networking costs there. Now, shifting gear, looking at the second biggest slice of that original pie we looked at, what's your cost centers? Storage cost becomes a very, very significant factor, very, very quickly. And there's really two different factors underneath the covers that you have at your option, two different knobs, if you will, in a cloud provider to control storage costs. First, obviously, is the storage category that you choose to use. Each cloud provider has different stratas of, uh, disk options based on performance and throughput metrics, availability, and things like that. And it's really up to you. You have to align that with your use case, your latency requirements, your throughput requirements. And another factor to consider is obviously cost. And then the only other option you really have is data volume. Again, most of these cloud providers charge for total data stored on a monthly basis. So like a high water mark sort of thing. So your options are, minimizing that data volume or maybe, optimizing your balance between the two by shifting some of your data, longer term data to more cost effective storage. Right. So again, these different things all impact that very significantly. Talk about the data volume there as well. There's really two different options when you're looking at Kafka. If you want to use a traditional deployment, again, the more traditional one where everything is local disk attached, it matches the traditional architecture. You really have different options of block storage, but that's what you're going to use for those traditional deployments versus these object only storage ones that I alluded to earlier and we'll follow up with in the next section. But for block storage, again, depending on what your latency requirements are, you can have latency and throughput requirements and IO ops and things like that. And there's different costs, right? Each one, for the best one, for example, 12 cents per gigabyte for the very, very best, provision volumes. You have an AWS plus an additional cost for provisioning. Second tier might be your GPS, your standard general purpose SSDs. They're still at 8 cents. And if you want to be able to leverage, your traditional spinning disks, high throughput optimized HDDs, and you can get those again at a fraction of the cost, roughly 50% less storage as well. So you really have your choice and you can control costs. Obviously, to optimize costs, you want to pick the right one that balances with your overall, you know, performance requirements. So sometimes you don't have a choice, sometimes you do, and you can pick the right one that makes sense for you. If you choose to do object storage and object storage only, or you want to do a tiered storage offloading thing, again, there's lots of different options available for you. Running the gamut from what's available in terms of performance, what's available in terms of costs, latency, those types of things, megabits per second. Just noting again that there are some additional costs related to the number of puts and number of gets. Usually these aren't very significant, but a very, very large use cases, if you read the data significantly, a significant number of times, these costs start to add up. So be aware of that as well. Whereas with block storage, once you write it, you can read it as many times as you want for free. Keep that in mind when you start accessing this data as well. But again, if you're using object storage, there's an additional latency incurred from getting this information available. So there's always a trade-off between what you want to do in terms of latency and performance and cost. There's always trade-offs to be involved in that regard. Now, if you look at just looking at these things from a bulk, 100% of the data stored on this particular platform, you can see that these are the different costs associated at different, again, throughputs per second, and assuming 1 day's worth of data being the most. If you keep data longer or have higher data volumes, these things definitely increase. But you can sort of see that, there's a significant difference if you use SSD only sort of local block storage using your, GP3 sort of standard use things. They're roughly 250% more expensive than object storage. Again, 8 cents per gigabyte versus 2.3 cents per gigabyte of storage. So obviously much more more, more expensive. You know, one of the benefits with our platform Stream Native's Ursa engine, which Kafka compatible engine, is that you can still get single digit millisecond latency while using an HDD based storage. So again, you can get a much smaller, you can sort of hit this blue line here where you're paid 4 cents per gigabit storage, still have a latency, significant latency performance SLA, and still have it 44% cheaper than an SSD only model. So if you don't want to go object storage, you have latency sensitive use cases, you can look at our option, our storage, and save you a significant amount of money. Now, how does that happen necessarily? How is that implemented? It comes down to our storage architecture within our platform itself. So a traditional Kafka deployment will read and write from one disk only, one attached disks. And that's going to be your GP3. It's the same class of disks. You can put them in an array, you can bundle them together, et cetera, et cetera. But at the end of the day, it's one mount point. The data is stored there, and it's one class of disk. Where with our storage layer, we have two. We have separated storage and compute, and we have separate disks for each one. And that way we have them optimized for one read, one for write path. So again, and one written for optimized for throughput. So when the data comes into our storage node, it is written first to an in-memory cache, very, very fast. Simultaneously, data is also written to what we call our journal disk, which is an SSD back class. So this is where you want to have SSD performance, and it's only used for backup, right? So it's written there, it's acknowledged there. If we have it on disk, it's persisted, we consider it acknowledged at this point. But we never read from this disk, only in the event that the entire node goes down and it recovers with the same disk, and then it can use that disk to restore the in-memory table. But in normal operational flow, all the data is written, was written to the mem table, is then consumed out into the ledger cache. We index it like a database, so you can have it for quicker lookups. So first we buffer it together, index it, and then periodically, you know, buffered it into a ledger disk, is made available there. And then periodically, once that memory table becomes full, we've gotten enough bytes together to make it optimized for throughput. We then flush that data to disk, and it's written there. So you can store, again, you have an IO path simply for writes, which is optimized for throughput, allowing you to use cheaper disk. While at the same time, you have an SSD for low latency write applications within the same architecture, allowing you to get a more cost-effective local storage over traditional Kafka deployment. Another strategy, obviously, is to optimize data placement based on time. So all Kafka deployments now have some version of tiered storage offloading. You want to move data from that is not going to be read right away or has lower latency requirements quickly from your storage nodes here, whether this is our bookkeeper layer or whether these represent local attached disks on brokers. It represents local disk only, very, very fast access. Over time, this data becomes, no longer available anymore. So as it becomes older, starts to age, it's less frequently accessed, and you can start shifting it to tiered storage, periodically. And there's a significant savings from that. You can optimize to that. So rather than writing directly to object storage, an option of having an intermediate buffer of data based on time to still serve your latency sensitive case, while moving the bulk of your data into tiered storage, the more cost-effective storage is still an option and a very, very great solution for most people, covering some of the different cost savings here. Vis-a-vis, you would save from moving, if you kept everything in disk, it's $4,500 or $4,000 rather. If you move everything to object storage, you basically save 90%. Extrapolate that over a month, for example, or just 7 days, it's a significant savings very, very quickly. So again, it's something to consider and something to employ. And it's very configurable within most platforms based on time. You trigger these offloads to make sure the data is available, but stored in a more cost optimized solution. Again, the trade-off being latency. Once you move this data to tiered storage, access and it becomes a little bit slower. In your more traditional Kafka models, there's a process that has to bring it back onto local disk first, and then it can be read from local disk. With our engine, we read it directly from the S3 storage into the memory cache, and so there's a little bit less of a latency cost with our solution versus other solutions, but it's still, as far as cost savings is concerned, true storage offloading saves you a significant amount of money. Another option is to, if you know your consumers downstream are not going to be necessarily Kafka consumers, right? So you consume it as a stream and you might want to read it as a table, right? Again, using an analytical tool, something like, Athena or Spark or Trino, or these query-based systems, these analytical tools that support a SQL interface, then it makes sense to utilize a lakehouse format, vis-a-vis Delta Lake or a Hootie or an Iceberg, Apache Iceberg format. All of these, employ some type of compression algorithm, a storage, a space optimizing format like Parquet to again decrease that storage size by a factor of 5x. In most cases, depending again on your compression, optimizations, things like that. So it definitely significantly reduces the cost of your data volume or the data volume of data, and then correspondingly the cost of storing this, whether it's an object storage or local storage, making it much more cost effective as well. And last but not least, another benefit of using a lakehouse storage is that you have a single copy of that data. So again, you have the stream table duality sort of concept where you can consume it, publish it as a stream coming in. So again, data comes in to a Kafka topic or Pulsar topic, and Stream Native, we support both. Streamingly write that data directly into a lakehouse format, which is configurable through our platform and some others. And then that one single copy of the data is available to be read by not only these batch analytical tools who support these lakehouse formats, but also you can read it back using a Kafka client and consume it as a stream again. So again, consuming it as a table or as a stream, and you have a single location. You don't have to replicate the data into a data warehouse. You don't do a change data capture through and replicate what your database table looks like in another analytical database table. You keep it in a single format, thereby eliminating duplicate copies, keeping everything in sync, a single source of truth, etc. Also has a savings benefit in terms of cost storage because you're minimizing the number of copies to one, and then everybody's accessing it at the same time. So again, you can save money using that feature as well. Now, last but not least, even though it's turned out to not be a very significant cost center in the overall Kafka architectures we saw in the original slide laying out, the cost centers were networking being first and storage being a significant factor. Computing is something to consider. It really, it comes down to two different factors, and there's lots of different people will publish different performance numbers and metrics and things like that. And so rather than getting bogged down in all of those details, you can really think of it as terms of throughput efficiency and provisioning efficiency. And so throughput efficiency really measures how many resources you need, how many cloud computing resources do you need in terms of cores and RAM to process a given number of throughput, right? So for 100 megabytes of throughput on this particular platform or that platform, what is my total spend required in infrastructure costs, right? So some platforms optimize for efficiency. Obviously, they'll reduce that number of CPUs and RAMs and things required. Things that are less efficiency will require more, and it will be reflected in your total spend in terms of infrastructure. Another equally, if not more important factor, as we'll see as the charts bear out, is provisioning efficiency, right? Measured as how many total percentage of computing resources that you've allocated that are actually needed, right? So again, if you over allocate, if you're provisioned for peak usage, and 50% of your infrastructure isn't being utilized as all, that's 100% wasted, and you're spending money on things that you don't need. And so your ability to optimize that, your provisioning efficiency will save you a significant amount of money as well, right? So looking first at how, again, looking at your TPE, your throughput efficiency, based on these theoretical numbers. There's some different numbers based on what you're going to get on these different platforms, and you can evaluate for yourself to do sort of a normalization on that. We do that in the white paper to compare some different numbers, but you can see again, even a significant 5x factor in throughput efficiency, even at very, very, at, at low numbers doesn't matter at all because there's a minimum requirement for 3. But until you even get out to like the 50 megabyte per second, isn't a significant savings. You're talking about a couple $100 versus maybe 1,000. In the big picture of things, again, that was like 6% or 8% of total costs. So it's not to say it's not important, but again, this is sort of a minimal cost. But you can see that that's your theoretical uh, gain overall. But then there's some things to consider as well that you might not take into account when you look at these platforms that are highly optimized, on computing. First being that these these specific solutions might require specialized or more expensive computing nodes than others. So again, like our Ursa engine uses a very standard M6 instance type, which are relatively inexpensive. If you switch to something that needs more memory or specialized computing resources, your per hour cost of those computing resources might be more, even though you use less of them. And another thing to consider, again, is increased licensing costs for these optimized solution, right? They may offset these infrastructure savings costs. If I'm a vendor, I want to monetize as much as I can based on your workload. That's generally how the business model works. So you have something that, if you have a platform that doesn't really use a lot of resources necessarily, sorry, you're going to want to, offset that to some extent, use it by increasing your licensing cost, so that for even moderately sized or larger workloads, you get to the benefit of that, having that data under your license. So again, take those factors into consideration when you're evaluating different vendor solutions, and bear that in mind. Last but not least, again, is the provisioning efficiency, and you want to maximize that, right? So traditional Kafka um, clusters would over provision. Again, this was to avoid the data rebalance and make sure you had all the brokers there available for when you needed to scale up. If there was a large spike in usage, you want to have the brokers already there. You want to have partitions assigned to them, so you could scale up very quickly. You didn't want to have to first incur that data rebalance, which again could take hours depending on the size of your data. And so you'd end up paying just over provisioning your infrastructure, and everything here in the white is what you're paying for that's 100% wasted versus what you needed in the light blue here. So having a platform that can dynamically scale very quickly allows you to sort of optimize this thing and eliminate wasted spend entirely. One of the best approaches for that is to choose a zero data movement technology that enables that. Again, Apache Pulsar, which is what Ursa is based on, has that built in natively at its lower tiers. Some other vendors have similar solutions, but at an additional cost because under the covers there's some additional specialization that's going on to avoid this. And so be aware that there's some additional licensing costs with this. But this is, again, optimizing your throughput, optimizing your provisioning infrastructure can save you. That's how you save money on computing resources. So summing this all up, the Kafka market has shifted quite a bit since it first came out. It's no longer just a technology; it's also a protocol, and people are starting to sort of see different Kafka offerings fall into sort of different categories. Highlight them here. So again, generally calling the serverless type, for lack of a better term, most vendors have some sort of version of this, where it's entirely, again, a hosted solution. You only, the broker and the objects, and you write only to object storage that entirely exists in the vendor's account. So you're connecting to this coming in from the outside. Dedicated or hosted is another option, again, where it runs. The infrastructure is all provisioned within your vendor's infrastructure, but it also uses a block storage, and it supports tiered storage offloading, so you can have low latency use cases supported. All your dedicated resources, these brokers are dedicated to you versus brokers were kind of a shared resource pool in a serverless model. And you can still offload to object storage. And then last but not least is sort of the BYOC or private cloud sort of deployment where all the infrastructure exists within your cloud environment, allowing you to take advantage again of like the private networking, right? So what are some of the again advantages of this? The serverless advantages again in green, and then the red are sort of the cons that I consider things to be aware of, the trade-offs you have to make. Like for a serverless account, it's pay as you go. That's great. So starting at zero, it's how they advertise these things. Only pay for what you need. They use cost optimized storage. Again, they're using the most cost effective storage. They've eliminated the data replication by using S3 or similar object storage mechanisms under the cover, so you don't have that networking cost. But you're still going to have to, you're going to pay a significant amount of money in networking, or somebody is, because that you have to access this over the public internet, right? So you're paying that higher the premium costs for data egress, and the more data you send out, the more it's going to cost you. Another trade-off is again, since you're going to object storage and there's an intermediate buffering of the data on the producer side, and again consuming it back out, there's higher latency that's going to be incurred. So again, low latency use cases are not going to be a great fit for this. And there's again limited scalability because it's a fixed serverless pool that's shared with everybody else. Your ability to scale up very quickly and have very large cluster is probably not supported in these types of environments. So those are some of the trade-offs with that type of offering. The next is in the dedicated version, you get a little bit better. So again, you have latency optimized storage, you have increased scalability available. It is a fixed cost, so these are resources spun up exclusively for you. So whether you're using them 24 hours or not, you're paying for them. Again, but it's in the cloud vendor account, so you're going to be paying that higher tier, that premium tier data access to get the data transmission out, the data egress out. But you are going to incur the data replication networking costs now as well, because you're using your traditional deployment model where you have brokers and leader follower replication. And as I mentioned before, you have the idle resources. So there's like a minimum fixed spend in these things, but you can scale up as large as you need, as well as these types of environments. And then last but not least is sort of the BYOC offering. Again, so this is something I mentioned that we Stream Native offer. Other vendors have like similar solutions to this. Allows you to use latency optimized storage. You have cost optimized networking here because now you can host your clients within your cloud account, within the same AZ, within the same region, and not have to pay that premium egress cost to access your data, consume your data as well. Theoretically infinitely scalable. It's your account, so you can add as many nodes as you want, as many brokers as you need. There's no really issue with that. But again, like the other ones, these are resources allocated in your account. Your node pools are going to be running 24/7. Your storage is available 24/7. So you're paying for that. You can't really scale down to zero in these environments as well. So there's sort of trade-offs, pros and cons with each one as well. But again, the problem is with these is each one of these is sort of an either or, right? So we talked about in the previous ones, if you pick serverless, you're going fully cost optimized. If you go BYOC, you're going latency optimized, and you're paying a higher cost for certain things, right? So, but sometimes you have different use cases that sort of require just cost optimization, right? I don't really need to have very low latency on this. I would just prefer to have some cost optimization for some of my data sets. Some of my tenants or topics don't really have strong ones. I want to just optimize on cost, but I still want to have, there's some that necessarily I need low latency use cases. I have very strict latency requirements. Traditional, you can either, most offerings are either serverless or dedicated. You can't really have, you can have one or the other. You really can't have both. What we have with with Ursa, something that we think is a differentiator is that we support both within the same cluster. You can carve out certain resources to belong to certain tenants, and some to others, and allow you to have, based on the quality of service you need in terms of cost, latency, choose the right solution for you, so you can fully optimize your infrastructure spin while not having to sacrifice one or the other, or have dual environments running up, one for cost optimization, one for latency optimization. You can still support offloading to lakehouse steered formats and make everything available, put everything in a longer term cost effective storage. And you can have, the best of both worlds in a single cluster, single management plane. Everything's available. So this is where this is sort of your optimal deployment, and you can optimize your Kafka spend accordingly. So with that, I know I've gone a little bit over. I want to thank you everyone for attending. If you want to get started with our Stream Native offering, I've talked quite a bit about it. Scan the security code here. We'll give you $200 in credit. You can get started, kick the tires on it, see what it's all about, test your Kafka applications, test your Kafka compatibility, everything with our particular platform. Also, if you're interested in getting a complete copy of my 400-page book, Apache Pulsar in Action, you can scan this QWERTY code here and get a copy of my book. No strings attached. Feel free to read it, download it, enjoy it. It talks more about the architectural differences, some of the the IO paths, for example, we talk about a little bit. Rebalance, zero data movement, all these types of things are covered in greater detail as well. And for those of you in the Bay Area or looking to travel to the Bay Area in the next week or so, we're going to have our data streaming summit at the Grand Hyatt in San Francisco. Please reach out. There's a few tickets left. It's almost full. Check out the sessions. Lots of sessions. Very big speakers from very big companies talking about their use of our platform to solve some of their data streaming problems. So definitely encourage to come. Training is also available to learn not only how to use our platform and the Kafka APIs and the Pulsar APIs, but also develop Gen AI and intelligent applications as well using our platform. And AWS will be there as a co-sponsor, or not co-sponsor, co-trainer in one of those trainings. So they will be there available as well if you want to learn how to use streaming data into the AWS Bedrock platform for machine learning. Definitely worth attending that session as well. And with that, I turn it over to any questions from the audience as well, or anything I might have missed.
Yeah, David, I know we only have a few minutes here, but one question is, what is the latency difference if we choose object storage versus bookkeeper?
Yeah, that's a great question. So within our platform, we buffer everything for 64 kilobytes. So before we publish that information to data, so we batch it up and buffer it internally. So it's really a function from the producer side of how long it takes you to produce 64 kilobytes, right? And until that buffer has been filled locally, and we're going to write it to S3 object storage, your producer is going to be, that data is not going to be available. So it's really kind of a function of your data publishing rate. If that makes sense. If you're producing 1 kilobyte a second, take you 64 seconds, necessarily to maybe have that data be available on your consumer side, for example.
Great, thank you. And one more, if you don't mind, we have a few minutes. How does Pulsar do automatic rebalancing, and how does that cost compare to Kafka?
Right, so there is no data movement in our auto balancing. So again, our architecture is completely stateless brokers from the beginning. So data and storage and compute has always been separated. That allows any broker to serve data from any topic at any point in time. And as part of the Pulsar architecture, we have automatic rebalancing across the brokers that happens periodically, regardless. It doesn't take a significant event for that to occur. So for every 1 minute, by default, the brokers sort of publish their metrics to our metadata store, and they look at one another and say, okay, what percentage of utilization on CPU am I allocated? What is the threshold for triggering an offload? So if one broker is at 70% CPU and the other two are at 30, it will decide at that point that it needs to offload some of its topics to the other brokers. It will release a certain percentage of its data and make it available. It basically unlocks it. It has a resource lock. It unlocks it. And then the other brokers can come in and take ownership of those topics and start serving that data right away. Our client is aware of that. We make it aware of that. We send that communication to the downstream client consumers to let them know we're switching over. So no exception is thrown, but rather it just becomes a reconnect on the client application side sort of seamlessly, and the data starts flowing again. So our goal is to minimize that impact entirely. You know, adding a new broker and getting data signed it takes about a minute. For example, so if you're just scaling a new broker, that would take you about a minute to get it settled in and start serving data. Again, versus like I showed the numbers for Kafka or in the matter of hours. But again, it's a function how much data has to be moved. And since we have zero data movement, it's very, very quick. It's very, 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 very seamless.
Great. Well, thank you so much, David, and thanks to everyone who was able to attend. I think that's all we have.
Oh, there's one more question. Can you explain
Oh,
what sharding is and what column issues are solved using this tool? I'm not quite sure I understand the problem. If the person who asked that question, I want to call it a name, wants to clarify, I could definitely address that one as well. It just popped up. Oh, they're not typing anymore. Um, I can sort of guess. So sharding, we don't have to do sharding necessary or partitioning of the data. We use a segment-based storage model underneath the covers for our Kafka implementation. So again, what that means is that, for example, one topic could store petabytes worth of data, but still only have one partition. So we don't have to shard our data and align partitions to match our storage implementation. And that implementation detail is hidden in our architecture. And so you only really need to with a Kafka implementation, it's really the storage is still the same. So what we've built is a stateless broker sitting in front architecture entirely. We still use the segment-based storage behind the scenes, and we support multiple protocols. So Kafka is one of them, Pulsar is one of them, MQ2T is one of them, JMS is one of them. They all have a protocol, and that's sort of a adapter, a protocol handler under the covers that speaks to the proper protocol to the clients. But from a storage mechanism, it's all the same, right? So you could theoretically publish to a topic using Kafka and then consume it from it using Pulsar or vice versa, because it's the implementation details is independent of that. And so with our Kafka implementation, data comes in, we store the data in segments. They're basically 50K message chunks. We have metadata storage that basically keeps a list, an ordered list of which segments make up a topic. And that way, any broker can then come in and say, now you're in charge of this topic. Go to that metadata store and say, okay, where's this data for this particular pointer, whatever cursor it is within that consumer? Go read it off of our storage layer and start giving that data back to the consumers. And you can do that, any broker can do that at any point in time. We do support partition topics, but you only really need that when you can't, the volume going into a single topic exceeds the capacity of a broker to handle it in terms of connections and IO operations coming in and out. At that point, you can add a partition to it, and under the covers, we implement it as a separate topic. But there's some management overlays that we know if you're treating it as a management topic, you're really consuming from multiple topics under the covers, and our client handles all those implementation details for you, connects to each one of those brokers serving that data on your client side and brings back data from each one of those partition topics under the covers for you. So hopefully that answers your question. If not, I'll be glad to follow up with you. We can talk as well through Slack or whatever as well. So hopefully that was educational. No other questions. Okay, yep. That was useful. Okay, thank you. I think no other questions at this point. Thank you everyone for attending. Hope you found this educational. So thank you so much.